Alright guys, so in this example here we have a nozzle with air flowing through it. So I'm going to start with a schematic. The nozzle will look something like this. And we'll have the inlet on the left and the exit on the right. So we'll call this 1 and we'll call the exit 2. And our working agent here is air. Now for our givens, we're given that the mass flow rate through this nozzle is going to be m dot equals 2.3 kilograms per second. Now, because you have one inlet and one exit, m dot 1 equals m dot 2, so I'll just leave it as m dot. We're told that we have an inlet temperature of T1 equals 450 Kelvin. We have an inlet pressure of 350 kilopascals, 350 kPa, and then a velocity coming in at 3 meters per second. Now, at the exit, we have a T2 equal to 300 Kelvin, so we lost some temperature there. We have a velocity which went way up, so we have V2 equals 460 meters per second. We're also told the ideal gas law, so I'm just going to label this a nozzle, by the way. We're told the ideal gas law is valid, so we have PV equals MRT at our disposal. And what else? We have the constant CP equals 1.011 kilojoules per kilogram Kelvin. Now we're looking for the area of the inlet, so we'll have A1 equals some number, and it's going to be in meters squared. And we're looking for the heat transfer between the nozzle and the surroundings, so we'll call that just straight heat transfer, Q dot, and it could be in or out, we don't know yet. And it's going to be some number in kilowatts. So let's start with part A. Part A is asking for the area of the inlet. So to find the area, I'm going to use the relation of this. So we have the mass flow rate equals the velocity at 1 times the area at 1 divided by the specific volume at 1. Now if I rearrange this for A, for the area, we'll have A1 equals the mass flow rate times the specific volume divided by the velocity at 1. And now we can start filling in what we have. So we'll set this equal to our mass flow rate of 2.3 kilograms per second. We have our specific volume, which actually we need to calculate using the ideal gas law. So again, remember we have P1 V1 equals MRT1. But if you divide both sides by the mass flow rate, you'll actually have that P1, these are flow rates, so I should have the dot up top. We'll have P1 V1, little v1, equals RT1. Now, rearrange for your specific volume. You'll have V1 equals RT1 divided by P1. And now we can figure this one out. So set this equal to, what is your gas constant? Your gas constant equals your universal gas constant divided by your molar mass. And your universal gas constant is, of course, 8.314. And your molar mass for air is 28.97. Your unit for your universal gas constant is kilojoules per kilomole Kelvin. And your unit for your molar mass is going to be kilograms per kilomole. So how does this cancel out? Well, your kilomoles and your kilomoles cancel out. You have a denominator in the top and a denominator in the bottom. So this would drop and this would raise to the numerator. Cancels out. And you're going to be left with kilojoules per kilogram Kelvin. So we have the gas constant equals 0.287. You might recognize that number. Kilojoules per kilogram Kelvin. This is commonly known, but I just like to show you where the number comes from. So we can set that into our your equation right over here. So 0.287 kilojoules per kilogram Kelvin times your temperature. What's your temperature is 450 Kelvin, and divide that by your pressure of 350 kilopascals. And now when you multiply this out, your Kelvin and Kelvin will cancel out. And now you're left with a kilojoule per kilogram up top, and then a kilopascal on the bottom. So the first thing we can do is cross out that kilo and kilo prefix, and now you're left with a joule per kilogram up top and a pascal on the bottom. And now, how can we break this down further? So what is a joule? A joule is a Newton meter, which is the unit of work. Divide that by that kilogram. And now that's all divided by the denominator of a Pascal, which is force divided by area, or a Newton per meter squared. Now we can cross out that Newton, and you're going to be left with meters per kilogram up top, but you're dividing it by 1 divided by meter squared, so you'll have m3 per kg. So that's your unit now that you're going to get out of this whole mess over here. So now when I multiply this whole thing out, I'll have that the specific volume at inlet 1 equals 0.369 cubic meters per kilogram. And now what I'll do is I'll go ahead and throw that into here. So I'll have 0.369 kilograms, m3 per kilograms. And we're going to divide that by our velocity at 1, which is just 3 meters per second. Now multiply this whole thing out. Your kilograms and kilograms will cancel out. And then we have a meter that's going to cancel out, turn into an m2. And lastly, we can get rid of our seconds, which cancel out over here. And we already got rid of that meter. And so now you're going to be left with meters squared. So we'll have area 1 equals 0.2829 square meters. And now for part B, we're going to be looking for the heat transfer and its direction. So we'll apply the first law of thermodynamics. So let's have that 0 equals the heat transfer minus the power plus the mass flow rate. And we only have one mass flow rate, so I'll leave it at that. Times this whole mess here of H1 minus H2 plus the kinetic energy here is V1 squared minus V2 squared. That's, of course, your velocity divided by 2. Plus your potential energy, which is just going to be gravity, times your change in elevation of Z1 minus Z2. All right, so how do we simplify this? So starting from the left, we know that we have a nozzle. We're looking for our heat transfer. And nozzles don't consume nor generate power, so we can therefore zero out our power. Next, we have our mass flow rate, which is given to us, and why don't we start this on a new line here. We'll have 0 equals your heat transfer plus 2.3, which is your mass flow rate, and that's kilograms per second, times, what is H1? Well, H1 is just your enthalpy at 450 degrees, or 450 Kelvin. 450 Kelvin has an enthalpy, a specific enthalpy of 451.8. So 451.80 minus H2. H2 is at 300 Kelvin. So it's your enthalpy at 300 Kelvin. You have 300.19. So minus 300.19. And of course that unit there was kilojoules per kilogram. Plus, what are your velocities? Your velocity at inlet 1 is 3 squared minus V2, which is going to be 460 squared divided by 2. And your units here are going to be meters squared per second squared. Plus, this unit here is going to be 9.81 meters per second squared, just gravity. And then Z1 minus Z2 is going to be 0 because we have a horizontal nozzle. So in that case, we can actually just cancel out that whole expression. And before we close our final bracket there, I just want to make sure that we're adding apples to apples here, because you can't add x to y, but you can add x to x. So we have to make sure that our unit here and our unit here are both consistent. So what is a kilojoule per kilogram? Well, a kilojoule is a kilonewton meter per kilo, and then you're dividing it by your kilogram. And from Newton's second law, what's a Newton? A Newton is a kilogram meter per second squared. So that's your Newton. And we're just going to multiply that by the Newton, add that kilo prefix, and divide by kilograms. So all I did was I just replaced that Newton with this expression here. Now we can cancel out that kilogram, and now you're left with, multiply across, you're left with kilo meter squared per second squared. So clearly you don't have the same unit here because you have a kilo meter squared per second squared. Here you have a meter squared per second squared. So to get from a meter to a kilometer, what do? You divide by 1,000. So let's go ahead and convert this into a kilo prefix. So we'll have 1 divided by 1,000. And now we can finally close our bracket. So now we just have to solve for Q. So we'll have that Q, or negative Q dot, is equal to this whole mess over here. Now if I plug that into my calculator, I'll have that it equals 105.4. And if I just get rid of my negative sign on our heat transfer, we're going to have that Q dot equals negative 105.4 kilowatts. And now if you remember, the sign convention just says that if you have a negative heat transfer, the heat transfer is leaving the system, and if you have a positive heat transfer, the heat transfer is entering the system. So because you have a negative sign here, that means that the heat transfer is leaving the nozzle, so heat is being transferred out of the nozzle as I predicted such. So therefore the answer would be from the air.